students, we have covered the solidification of the casting process and learned various aspects of nucleation, different types of nucleation, and the effect of cooling rate in determining the shape of the grains and the size of the dendrites which are formed in the solidification of casting. As I've told you earlier, the solidification mechanisms developed for casting, the scientists have utilized similar solidification mechanics in the solidification of welds or the welded structures. But there are certain differences in the welding solidification, and those are arises due to different factors or points to consider. The first one is the dynamic nature of welding process. The welding process is somewhat different as compared to the casting process because there is a movement of the heat source and all such dynamic nature of the welding process. Either the movement of the workpiece or your welding torch is moving to perform the welding process. So you have the dynamic change of your heat source from one place to another place. So the temperature is also changing, the temperature gradient is also varying. This is the point which somewhat changes the solidification of your welded structure. And then we have the unknown molten weld pool shape. We have discussed the weld metal transfer modes and observed that the size and the shape of the molten weld pool. If you increase the temperature, then you can change the molten weld pool shape, and the heat input determines the solidification or the microstructure in the welded components. In the casting process, we observed that either the homogeneous nucleation is taking place, or in most of the cases, heterogeneous nucleation takes place in order to form the crystals and grain growth which occurs in casting process. But in solidification of welding, we have another mechanism which is called epitaxial grain growth or epitaxial nucleation of the grains. It is a kind of heterogeneous nucleation only observed in the solidification of the welded components. So we will discuss this epitaxial nucleation of grain growth in our next slide. Then we have the variation in temperature gradient and growth rates within the molten weld pool. There is a change in the growth rate within the molten weld pool, and also depends upon the type of the welding process and the way you are performing your welding process. The procedure also determines the variation in the temperature gradient. Suppose we talk about the welding performed with the help of bare electrodes or the coated electrodes, you also can understand that there is a situation of large temperature gradient when you are using bare electrodes, when there is no flux which forms a blanket of the slag. The slag covers up the molten weld pool and serves as a blanket which lowers the temperature gradient between the molten weld pool and your surroundings. These are some points which makes a difference between the welding solidification and the solidification of the casted components. And in welding solidification mechanics, the important parameters which influences the microstructure of are the temperature gradients represented by G. Then we have the growth rate denoted by R. We have also discussed that what is undercooling. Finally, the most important part is the alloying composition. So alloying compositions also determine the microstructure of the welded components. This liquid temperature gradient denoted by G, it will be equals to del T by del X. So it is the temperature gradient within the liquid molten weld pool, and the solidification rate is denoted by R, which is the dx by dt. So there is a linear change in the dimension of the solidified part. So how fast it is solidifying, that is our solidification rate. Now if you multiply these 2 points like temperature gradient and the growth rate, you will get the cooling rate. Then we have already discussed that temperature gradient in the liquid is very important because it dictates the nature of temperature field in advance of solid liquid interface. So whatever be the temperature gradient in the solid liquid interface, that will be your GL, and the solidification rate dictates that how fast the solid liquid interface is moving, means how fast your solidification is propagating inside the welded zone. And later on, this G into R component, it will have an influence on the dimension of the solidification substructure such as the dendritic arm spacing. So if this GR value is very high, then the dendritic arm spacing means that the spacing between the two dendrites will be less compared to whenever you have a lower GR value. And in case of this welded molten weld pool, all these factors like G, R, and del T, they vary from region to region and process to process. Within the same pool or in near the vicinity of your molten weld pool, there is a change in the value of G and R and T, del T, and it depends upon the process to process. Therefore, microstructure which develops in the welded metal varies noticeably from region to region. This gradient temperature is also varying from different locations. In solidification, the solute is also getting rejected. So that causes the segregation of these metallic components or the elements. And all these factors determines the microstructure of your solidified welded part. If you can see, this is the drawing which shows the fusion zone. Above and below it, there is a base metal. They have represented the central portion of the weld bead, and the welding is carried out in this direction from right to left, and this part has already been solidified. You can observe that there is a variation in the microstructure. Near the base metal, you can say the zone from which the solidification is propagating in this direction, because the heat source or the metal weld pool is moving in this direction. So they are inclined into this direction. You have different types of microstructure like planar microstructure, then you have a cellular microstructure which further is broken into the dendritic microstructure, and within the dendritic microstructure you have the equiaxed dendritic microstructure. If you see that here you have larger value of R and smaller G, so the temperature difference, you can say the temperature gradient will be small and your solidification rate will be fast. The solidification value, this small temperature gradient and solidification rate, and the larger temperature gradient, because this is more close to the base metal and more of the heat is being transferred at a very rapid rate. I told you that the solidification rate or the cooling rate determines the microstructure in the welded structure from different location, from region to region. I told you that another important type of the nucleation or the different type of nucleation is happening in case of the welded structure, which is your epitaxial grain growth or epitaxial nucleation. This word is derived from a Greek word called the epitaxis, and its meaning is to grow from your grains within the weld pool or in the solidified zone. It is growing from some particular nucleation sites. And what are those nucleation sites? In this particular epitaxial grain growth or nucleation, the atoms from molten pool solidifies on the pre-existing lattice sites of the adjacent solid base metal. What is happening here? You have this base metal, and this particular zone is your solidification zone in the welded seam, and the welding is progressing in this particular direction. From this figure you can observe that I'm talking about this small zone, and it has been represented in this particular diagram. You can see that here in the base metal near the fusion boundary you have the grains oriented like this. Whenever the welding is performed, these base metal grains will be partially or fully melted. They give the preferential nucleation sites for the growth or the formation of the crystals within the molten weld pool. Earlier, in case of the solidification of casting, nucleation was occurring on the mold wall. So particles present on the surface of the mold wall, those special particles, in most cases either they may be of sand casting particles, or if you are talking about some permanent mold which is having the higher melting point than the metal to be casted. So their sites were the mold wall surface, and here in this case of welding, the base metal surface which is partially melted, those sites or grains will give the preferential sites. And in the fusion zone, a preferential orientation develops in which the grains are roughly perpendicular to the boundary of the weld interface. You see, this is the fusion boundary and the grains are roughly perpendicular to the boundary of the weld interface. So this is your weld interface, and you see these grains are roughly perpendicular and they have grown from the solidified or partially melted grains from the surface of the base metal. They grow in a spatial direction. The grains on the surface of the base metal, they are oriented in a spatial direction. If you remember, in case of material science, cubic structure, there are different atomic planes. Those base metals, you can say the grains of the base metals which are oriented in this particular 100 direction. So you see that there is a cubic plane and this plane is 110 direction. This particular crystallographic direction is the direction of those crystals which have nucleated from the surface of the base metal. And why these new grains are developing in this direction? Because as per the mechanics or the metallurgy, this particular direction is the easy growth direction, and it has been observed that solidification is most efficient in this particular crystallographic orientation. That has been reported as per the observations by the scientists who are the metallurgists. They have observed that the growth of new grains present in the solidified region, they are aligned in the direction of 100 crystallographic plane, because this particular direction is the direction of easy growth as compared to other directions. The scientists have observed that the growth of newly formed crystal and the grain growth is favorable in this particular 110 crystallographic direction. This type of nucleation or grain growth within the welded component is known as the epitaxial grain growth or epitaxial type of nucleation. It is a special type of heterogeneous nucleation in which the pre-existing sites or the grains are present on the surface base metal. They provide the preferential growth sites to the nucleation of new crystal within the solidified section of your weld pool. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.